Hi, my name is Miloš and welcome to Element 14 Presents. Today we will be talking about motor drivers, we'll design our own custom PCB from scratch, and in the end we'll talk about PID controllers. Let's go! In my hand I have a simple brushed DC motor, and the easiest way to control it is to just connect it to a power source. So pretty much just simulating a battery, and if we connect it, it's spinning. So is that it when it comes to motor control? Not even by a long shot. If we take a look at a project like this one where I designed a whole mobile robot platform with a robot arm on top, different motors actually have different requirements. For example, these wheels here need to spin at constant speeds for the robot to do certain movements, while these motors here in the actual robot arm need to go to set positions and keep those positions. So what's actually behind all of that? How does the electronic behind that work? That's something that we'll be exploring in this video, and then we're gonna design our motor drivers that at some point will get to go into this. So let's first begin with the simplest motor driver. Let's look at drawing brushed DC motors. The most basic way to make a motor spin is by simply connecting it to a power source like 12 volts. A way to control this more accurately would be closing and opening a mechanical switch. To control this electronically, we have a few options. We essentially need an electronic switch. A relay is a great option for simple on and off control, but to control the actual speed of the motor, we need to use a MOSFET because we need higher frequencies. Relays don't really play nicely with higher frequencies, while MOSFETs are great at it. To control the speed of the motor, imagine toggling the switch hundreds of times a second. By varying how long the switch stays on versus off, we create a pulse width modulation or PWM signal. A wider pulse delivers more power for a faster speed, while a narrow pulse slows it down. Because we need to switch high currents at very high frequencies, an N-channel MOSFET is perfect for the job. It acts as an electronic switch that turns on when the gate pin reaches a specific voltage relative to the source pin. There is a bit more to it, but for now this is all you need. In an example, I will show you a circuit with an IRF Z44N MOSFET. Its gate source threshold voltage is 20 volts. Since our microcontroller can generate a PWM signal at 3.3 volts, we need something in between to drive that MOSFET at the appropriate voltage. The proper way of doing this would be using a dedicated MOSFET driver IC, but for this simple test I will use the LM258P op-amp configured as a comparator that will act as a level translator to drive the gate of the MOSFET with over 20 volts, while the Pico will be at 3.3 volts. Let's take a look at the circuit on the bench. Here is the circuit that you've just seen in the drawing. Here is the MOSFET. Here you can see it up close as just one example of a package they come in. That's it here. We have an op-amp that's driving that MOSFET, as you've seen in the schematic. And I just have a simple microcontroller here that's connected to a potentiometer to just control the duty cycle. So if I turn on the power supply now, the motor is standing, and if we slowly increase, you can see that the motor starts spinning, and if we continue turning the potentiometer, you can see the motor spins faster and faster. And this is the top speed that you can reach with this motor at this voltage. And of course, we can tune it down so that it's barely spinning. As you can see, it's barely spinning now. And yeah, so that's one way to control a motor. But if you take a closer look, the motor is just spinning clockwise, and there really is no way to switch the direction of the motor driving besides flipping the wires around. Is there maybe a solution for that? If we would have used just MOSFETs for this robot, it could only go forward and maybe turn if we spin one side faster than the other, but that's not what we really want. We want the robot also to be able to go in reverse, turn on the spot, and so on. Also, for these robot joints in the robot arm, we want them to be able to swivel in both directions. So for something like that, we need the actual motor drivers. Here you can see an example of that, and they can spin motors in both directions and also change the speed. So how do they work inside? Let's take a look and then we can test it out. As we just saw, a single MOSFET gives us precise speed control. However, it only allows current to flow in one direction, meaning we can't reverse the motor spin. To get both speed and direction control, we need to arrange 4 MOSFETs into an H-bridge configuration. This setup allows us to electronically flip the polarity of the voltage going to the motor. we control the bridge using two signal lines. The signals on one side of the bridge will never be high at the same time, since that would essentially mean that all of the current would pass through those two MOSFETs and not the motor. MOSFETs have low on resistance, so this would act as a short circuit, and we would pretty much fry the chip. This is why these negations are here, just to show that in the driving state, if one of the MOSFETs is on, the other must be off. In total, this gives us 4 possibilities, but we are interested only in the 2 of them. If both signals are low or both are high, no power flows across the motor. Instead, both motors' leads are effectively tied to ground or to 24 volts in this case, which won't spin the motor. We are interested in cases 2 and 3 where the two sides of the bridge are different. If signal 1 is low and signal 2 is high, the current flows this green path, spinning the motor in one direction, let's say clockwise. If we flip the logic so signal 1 is high and signal 2 is low, the current takes the yellow path, reversing the motor. By applying our PWM signal from earlier to the active high line, we unlock full control over both the speed and the direction of the motor. Let's see that example on the bench now. So instead of the MOSFET, we're gonna use the H-bridge now to drive the motor. This is just a motor driver module, and it's a dual H bridge motor driver, so you can drive 2 motors with this single module, and this is something that we will recreate during this video, as you will see. So the idea with this is that instead of one input signal, we have 2 input signals, as you've seen the yellow and purple wires here. So we either drive one of them and the other one should be pulled to ground. So if we do that, if we turn the potentiometer to one side, turn on the power supply, we can spin the motor in one direction. And if we keep spinning the potentiometer to the other side, it first slows down and then it starts spinning to the other direction. So essentially with this we get full control of the motor. So for our motor driver, the one that we will be building now, we want some kind of an H-bridge, and since I want to control 2 motors, we will need a dual H-bridge motor driver, something similar to this. We've now seen how MOSFETs can drive a motor and also how motor driver works, and in this robot here at this stage, so for the wheels themselves, I'm using actually 2 of these. So what's gonna be the actual project for this video? It's actually designing a custom motor driver that's pretty much better than this in every way possible. There are of course other motor drivers that you can use that you have probably used that are great, but I wanted to design my own custom PCB with certain requirements. I'll also take this chance to show you my whole engineering process of how I actually come up with an idea, how I go through the whole process, and how in the end I evaluate that idea and iterate into next versions of that same project. So let's begin with the requirement list. I will now show you my process for going from the idea to the finished project for a more complex project like this. So first of all, I make a requirements list for the PCB when we're talking just about electronics, or a bigger requirement list when it comes to a bigger project like a robot. So for the PCB, that would include what kind of voltages I wanted to work with, what kind of motors for this version of the PCB, and so on. So for this project, for this PCB, I want to drive 2 motors. I want it to be a single PCB, not like a motor driver and an MCU and then you need to connect them. I want everything to be on a single PCB, to be as compact as possible. I want to achieve at least 5 amps peak current per motor, so that's 2 motors, 5 amps per each motor. And I want a really wide voltage input range. What that means is that I want to be able to power my project with anything from 5 volts to 36 volts without thinking if the other electronics can handle it. I want to pick the voltage based on what I have at the moment, like battery pack, power supply, and based on the motors, and not think about the rest of the electronics. Maybe we can even push that range further, we will see as it goes. I would love to go above 48 volts as well. And also here are some other things that you can see on the screen. So like clean free power for the measurement stuff like current, so we want to have an LDO there and so on. For a project like this, when you outline all of the requirements that you want to hit, I also assign some priorities. I would begin by looking at components. So the main component here will be the motor driver IC, since this will be a motor driver project, let's say. And I would go to somewhere like Farnell and pick out just in the filters the parameters that I want this driver to satisfy. So that would be a brushed DC motor driver, 2 outputs, but be careful, sometimes 2 outputs, some manufacturers look at that as literally output pins. So these STM motor drivers can handle 1 motor with 2 output pins, let's say. Also the current and the maximum voltage rating. And through that I came across these Texas Instruments motor drivers. They're kind of expensive, but they really do everything I want and are a really small package for what they are, so they fit perfectly. Next thing from there would be to go for the datasheet, check the RDS on resistance, which is rather okay. They can handle 3 amp continuous per motor, 6 amp peak. There is even a much powerful version of this, but don't need it for mostly for the projects I work with. So this was a rather nice choice for my project. From there you need to look at, if you choose this chip, you need to look at its requirements. For example, this chip needs 12 volts power always for the supply voltage pin for the internal logic, things like that, which means we need those 12 volts whatever the input voltage of the actual PCB is, so we need the buck boost converter and so on. I'll show you how all of this looks in the EDA tool next, but this is just for you to get an idea of how the whole process looks of going from the idea, forming this requirement list, and then designing and testing everything. The requirement list is a really nice thing to have since it keeps you on track and it reminds you of the things that you want to achieve, and it's a nice way to just tick off stuff like with these checkboxes here when you know you've completed something, and when you do revisions then you can fall back onto this and see if you've missed something and how you did it and so on. So let's jump straight into the EDA tool. Time to look at the electronics. So we're gonna start with the schematics and then go over to the PCB. And let's begin with the motor driver that you've seen me pick. So these are all of the components necessary around it. I won't go into too much detail. So how I do something like that would be find their typical application reference design in the datasheet and follow along with all of the recommended calculations, component placement, component choices, and so on. Besides that, we have the 2 current sensors here. So for each motor I'm going to use a Hall effect current sensor because they're a bit more stable than just shunt resistors. And here we have just some random capacitors that are also needed. On the power electronics side, as I've mentioned previously, we will need something like this. So this is a buck boost converter. The motor driver IC needs 12 volts and we need to provide those 12 volts whether our input voltage is 4 volts or it's 40 volts. And this is where this thing comes in. You just adjust the output voltage using these 2 resistors. There is a simple calculation from the datasheet, and you can set at what voltage it starts working using the under voltage lockout using these resistors here. Now the chip is rated to work from 3 volts to 40 volts. I tried setting these up so that it works from 3.3, but it's stable from 4 volts, so it is what it is. Not really working from 3.3 volts, but I'll take working from 4 volts to 40 volts. And of course, if you're going for it to work at 40 volts, ensure that all of these capacitors that are at the high voltage side actually rated for those voltages. Besides that, we have the power connectors, which are daisy chained. These are really cool connectors. There are XT style connectors. If you've seen those style of connectors in RC cars and general RC models, but these connectors have additional pins for communication that I'm gonna be using for I2C. I added a simple fuse on the board here and also added a voltage divider so that we can actually measure the voltage, the input voltage with our microcontroller. Besides that, so we have the output from 12 volts. We also need the 3.3 volts for our MCU and other low power stuff. To get that 3.3 volts, the easiest way would be to just drop the 12 volts directly to 3.3 volts, but I decided to actually do it in 2 stages. First with a buck converter to drop it to around 5 volts. Doesn't have to be exactly 5 volts, but 5 volts is an okay number since we can use it for other stuff, maybe in the future. So you can adjust the output voltage with these resistors here. And then we drop that 5 volts to 3.3 volts using an LDO. LDO, imagine it as a smart resistor that changes its resistance so that you get a clean, nice output of 3.3 volts in the end. at the output, and it's a much cleaner output voltage compared to just a standard buck converter. So this is why the additional component count, even though we can achieve similar results with a less number of components. In the end, we have the microcontroller that I will be using, which is a Pico 2, and I didn't have time to do a custom layout, so I just put a Pico 2 on the actual PCB, as you will see shortly, and added some cool stuff like these switches, which I will be able to control through software to enable or disable pull-ups for I2C. Also added an RGB LED so we can do easier debugging, and at a glance you can see whether your PCB is working or not. And it's controlled over I2C using just a small IC and a bunch of connectors for connecting everything else. Now, the actual PCB you can see here. It's 50 by 60 millimeters, so not too bad, not too large. And that size is mostly because of the MCU that you can see that needs to fit here. But yeah, it's a rather compact design. We have the motor driver here with its connectors, some big capacitors, other power connectors for daisy chaining, the fuse. We have the whole buck boost circuit here in the middle, and a bunch of connectors. And on the other side we have the MCU and some other components that just couldn't fit. If we take a look at the 3D view, this is how our PCB will look like in the end. So we just solder our Pico 2 here, and this is just a platypus here because one of the projects that I will be using this board in is my platypus bot that you can also check on Element 14 community. So yeah, this is how the whole PCB looks like. The only thing left now is to solder it, which will prove to be a rather fun experience considering this chip is okay, but this here, as you can see, there are no visible pins here. That's how it's in real life as well, so you really need to solder it by feel, but you'll see how it goes. Before we start soldering the PCB, I want to share another tip with you, and that's another checklist. It's a bunch of checklists, but trust me, they'll save you a lot of time in the long run. So what this checklist is that I go through my EDA software and make a step-by-step guide literally for me on what I need to solder, in what order, and how to test it. And this is especially important for new designs where you're pretty much not sure what's gonna work and if anything is gonna work. So for example, for this board, I started with the buck boost converter, then I went to the buck converter, then the LDO, that followed by the motor driver, and I would test each segment step by step, as you will see in the upcoming clips. So yeah, this is a really useful way to actually keep yourself on track when you're debugging a PCB like this, especially when it takes more than a single soldering session. And it's a nice way for you to also write down any errors that you find along the way, as you will see later in the video. Here you can see the progress I'm making with the board. I already soldered a bunch like the buck boost, the motor driver. I'll show you the motor driver later. Now let's focus on the power. So if we turn on the power supply, you can see that the 3 LEDs have lit up, and now you can check the multimeter. The ground is connected at the power supply side. So if I probe the small test points here we have the 12 volts. Here we have the approximate 5 volts, we don't need it to be exactly 5 volts. And here we have the 3.3 volts. So all of the power rails are working. The motor driver is also working, as you will see in the next clip. And then we can continue on. Okay, so we have already tested the power supply, and you can see the board is on by the glowing lights. Let's connect the motor to one of the motor connectors. I'll just use some alligator clips, and I'll show you one of the H bridges. So as you can see on your screen, I still haven't soldered on the microcontroller, but we can spoof it using a piece of wire. So we want the 5th pin from here, and we want to connect it between 4th and 5th pin on this side here, which is connecting the reset for the PWM bridge and one of the channels. So if I do that now, just get the wires in place. You can hear the motor is spinning. Let me turn up the power supply so we don't run into the overcurrent issue. And if we go again, you can see that it's working. It's also working for the other H bridge, and if we go the other PWM route, it just flips the direction around. So we're just going nicely along the checklist. And our PCB is finished. I'm extremely happy with how it turned out, and I'm really happy to report that 98% of the PCB is working, but there are some issues that I managed to identify because of the checklist. So I stayed pretty true to the checklist. You won't always follow it step by step, you won't do all of the tests always, of course. But it was a really nice way for me to write down, for example, a wrong footprint and also a pin that was tied not in the way it was supposed to, and it was burning out a chip, as you will see in the system requirements update in the next clip. But yeah, I'm really happy with how this turned out, and when we compare it to the motor driver that we started with in the end, it is a bit bigger, but it's a lot more capable, has an onboard MCU, a bunch of connectors, wider input voltage range, and so on. So let's go through the system requirements, see how we actually did, and then we can go and fully test out our new PCB. It's time to go back to the requirement list and to the Google Sheet so we can fill it out a bit. I've did that beforehand, so you don't have to wait for me. So let's go step by step. All in one unit, everything is on a single PCB, so we can say that that is completed. Wide voltage input range, we've said that we want anything from 3 to 36 volts. What I did manage to test is that it's stable from 4 volts to 31 volts. Even though the IC says 3 volts is the minimum working voltage, the buck boost, it's not really happy there, so still gonna take this as a win and should be able to handle 40 volts without any problem since everything is rated up to that voltage. So for the dual brush DC motors, the motor driver handles that great. We have dual current sensors, no onboard MCU as you've seen. I've only went with the fallback MCU, so we do have that. You've seen that I've doubled all of the power connectors and communication connectors, so you can literally just daisy chain multiple of these PCBs in a project and not have to have a dedicated cable for each one of them. Compact design, I would say it can go a bit smaller with the custom layout of the MCU, but still 50 by 60 millimeters, rather happy with it, especially considering the number of connectors for expansion that I have on it. Input voltage measurement was an easy one. For the temperature, I don't really have built-in temperature sensing as I planned initially, but I do have over temperature warning, but still we won't count that as completed. So for the connectors, we can say that everything here is checked. Since there are a lot of connectors, the power is really clean for 3v3 because we have an LDO. So we go from the buck boost that this gives you 12 volts to a buck that gives you around 4 volts to an LDO that gives you 3.3 volts. So in the end we have really clean 3v3 power. And debug LED, we have an RGB LED that we can control over I2C, so we're not even using a bunch of pins there, just the I2C that we're already using. So that would be it on a requirement list. There are of course things that can be improved. From there I also added an errata sheet. What this is, it gives us a clear overview of what's wrong with the board through testing. And as I've already mentioned, there is the problem with the wrong layout for the RN2905 ICs. The footprint is too big, so I can either check if there are these components in that footprint or change the footprint on the actual PCB. And also for the buck converter, since the enable pin can only go up to 6 volts and I've driven it with 12 volts, but in the end it doesn't even need to be driven since it has an internal pull-up, so that wasn't even needed. I also added a command sheet here that covers all of the commands that are currently integrated, G-code style commands with examples on how to use them. I find this really handy because when I switch from project to project, I just get back to this document and I can get it going rather quickly. And another thing that can be really useful for you if you're trying to recreate it is a full PCB BOM. So if I just decrease the size here, this is the full bill of materials for a PCB with everything that I've used here, all of the resistors, their designator where I've got them, so mostly at Farnell, but I also put alternatives here and just check for my own sake if something is in stock and so on, based on all of the parts that I have or not that you can see here in the background. So yeah, the requirement list was a really useful thing, and now this Google Drive, this Google Sheet link will be shared both on GitHub and Element 14 community if you want to continue work on this project. I won't be spending too much time on software since it's still a work in progress, but I'll just cover what it currently does. So the whole idea with this PCB is to be the low-level hardware layer for my projects. So for example, if we have a robot like you've seen in the beginning that has 4-wheel drive and we need 2 of these, there won't be any custom like algorithms or higher end algorithms on these PCBs. They will just execute commands given by higher computing power like a Raspberry Pi 4 or NVIDIA Jetson or something similar, which will just send commands like go to that position or set that motor to that speed and so on. How we actually set those speeds and positions is something we will cover next. But yeah, there is just a bunch of files where you can set, for example, here the pins and different kind of parameters. There is also a few PIDs, so for the position and speed. If you don't know what PIDs are, you'll find out rather soon in this video. And in the end, I asked actually Codex to generate a graphical user interface, and it did an amazing job for that. So using this interface, you'll be able to easily test out your board to see if it works nicely. It's just essentially a Python script that has a nice visual overview and just sends those commands over serial, but also we'll be able to see if our PIDs are properly tuned. So if you don't know what that means, you're gonna find out now. Okay, so I have 2 motors connected to my PCB here, and everything is connected to the power supply, and we're at 3.3 volts currently, so let's turn it on. You can see that the board is actually turning on with the RGB LED flashing in all colors and now in solid colors, and you can see all of the voltage rails are active based on these 3 LEDs here. Now if we click refresh ports and select Pico 2 and connect, we are now connected to the PCB. Is there a chance for these to work at this low voltage with these motors? Probably not, but we can try because these motors are rated at 24 volts and 12 volts. So for example, if this is for bridge 0, if we enable that bridge and try driving it, you can see that it's barely starting to spin the motor, and you can see that the current has increased because the voltage is just too low. But if we try increasing the voltage on the power supply, you can see that it just starts spinning, and also that the board is working the whole time. You can also see that the color of the RGB LED has changed to blue because one of the bridges has been enabled, and if we enable the other bridge as well, it will change actually to purple. So let's test the voltage range. We're currently at 5.3 volts, so let's go to 31 volts. This is up to 12 volts, but yeah, nominal 12 volts, but it will survive a quick test. As you can see, it's working rather nicely, but let's get it back to 12 volts so it doesn't burn out, and we can stop. Also, another thing we can do is enable both motors, drive and drive. So you can see that the both motors are spinning. We can also spin motors in different directions, control their speed, and so on. You can see how different the gearing is between these two motors. So this one has much more torque, but this one is rather quick. So we can stop this one and go to the nominal voltage of around 24 volts for this motor and control it in the same sense. So yeah, our PCB is actually working rather nicely. We have both controls of both motors at the wide voltage input range. At 3.3 volts it's not that stable, it's stable at around 4 volts, but still a rather nice range, and it goes nicely with the system requirements. But as you can see here, there is an encoder attached to this motor, so we can actually control speed and position of this motor. Let's see how we can actually achieve that through PID controllers. Now that we have fully tested our new PCB and know that most of the system requirements are fully met, it's time to do a bit more advanced stuff with it. So for now we've only controlled the motors, just driven them with different duty cycles. But what about something that we mentioned in the beginning for robotics projects like this? What if we want to put this motor at this position or drive this motor at a certain speed? Then we need something called PID controllers, or proportional integral derivative controllers. What they are and how they work is something I will explain to you now, and then we will see how tuning of the PIDs goes and the results that we can actually achieve with them in the end. Let's take a look at how a PID controller works. PID stands for proportional integral derivative, and I'll get into the specifics of each one of those later. So let's first imagine the PID controller as a black box with some inputs and outputs. Two inputs, so reference and a sensor, and just some kind of an output signal. In our case, we will give it a speed reference, the speed measured by our encoders, and a PWM duty cycle that will go to a motor drive. But what's actually happening inside this black box? So here is the diagram of that. We have the three components PI and D. We are summing them and getting them to the robot or to our actuator. We are reading the encoder signal, then in a piece of code we are converting that signal to the speed measurement, and then we're subtracting that speed from our reference, getting our error signal. The idea and the purpose of the PID controller is to actually minimize that error, ideally to have it at 0. Now let's take a look at each component of the PID controller. So as I've said in the beginning, we have the proportional part, the integral part, and the derivative part. The proportional part is the simplest one. This part adjusts the output based on the gain and how far you are from the reference. So you can imagine if you want to go at 100 kilometers per hour and you're going 50, for example, you're gonna press the throttle more than if you were at 8. The integral part of the controller works by using the integral gain and the accumulator is just the sum of all of the errors so far. It really helps with correcting the steady state error. So for example, if with the P controller you get to around 95, the integral part will get you just right around to the 100, as you will see later on in the video. And in the end we have the derivative part, which works with how fast the error is changing, and that helps with overshoots. The actual output of the PID controller is the sum of these three components and is represented by this formula here. Now, this is just some random math now on your screen, so I'll try and draw you a graph to get this a bit closer to you so you understand how it works. So here is our graph. The yellow line is a reference, so we just want at some point our speed to jump from 0 millimeters per second to, for example, 10 millimeters per second. Doesn't really matter the number. Ideally, our controller would follow this reference completely like this with 290-degree turns, but that's impossible, as we will see. So let me first draw how a P controller would look like. It would be something like this. And as you can see, it increases the speed when the reference jumps, but it never actually reaches that reference. There's always that steady state error. Now, if we add the integral part of the controller, we would see something like this. The signal would rise a bit faster and we would have no steady state error. but you can see that we have a bit of an overshoot here. If we added the derivative part too, and this is of course if everything is properly tuned, we can then lower that overshoot and get a controller that follows the reference much better. And when I say tuning the controller, that just means adjusting the proportional, integral, and derivative gain and see how your output looks like. Now, because of non-infinite acceleration, you can never get an ideal controller that follows the reference, especially for step references. But they work really good, especially for real systems, and I'm gonna show you an example of how this works with our actuators. We have our 12 motor connected to our board as well as the magnetic encoder, so let's finally test out PID controllers and how they work. So this is the panel that will let us do that with PID controllers, but before that we need to connect to our board. It's this port here, and you can see that we are connected. Before we actually do any testing, we need to make sure that the motor is spinning in the direction that we want it to spin. So for example, if we just drive it with some small drive like this, you can see that it's spinning. But as if you look at the position, you can see that the position is actually falling, which means that the motor is spinning in the opposite direction of what our system is actually expecting, so the PID controller. So if we click self-check detection, it will check that and it will correct it. So now when we click self-check direction, it will spin the right way. And if we try spinning it, so just enable this, if we try spinning it in the positive direction now, you can see that the value is now rising. So we've got that all taken care of. Next thing we can do is test out the speed PID controller first. Let's set all of the values to 0 and let's change to speed PID, apply mode, and change the data to speed. So this was the speed from some of these movements, and now the speed PID controller is active, but as you can see nothing is happening with the motor. That's because the reference is 0. Let's say we want to spin at 4000 counts per second, which is a little less than 1 revolution per second, and as you can see nothing is happening because all of our gains are 0. But if we put this gain to 0.5 for example, you can see some movement and that the motor is doing something but nothing too nice. Let's decrease it. You can see how the oscillations seem to be a little bit less, but we need to decrease it more. Something like that. And now if you remember the drawing, you can see that the motor is spinning at some speed, but it's actually not reaching the reference speed, which can also be seen if we increase this value to 8000 for example. You can see that the motor tries and jumps to spin at a higher speed, but it's actually not reaching the reference value that we want. Now if we add a bit of the integral part to this, like so, you can see how now it follows the reference much nicer. This is rather noisy because it's running at rather low frequencies at 250 Hz. That's the fastest I can get this encoder to work reliably. So it won't be too accurate, but you get the idea. We can also flip the direction, and you can see how it transitioned from 8000 counts a second in one direction to the other. We can of course adjust further the PID controller. These are some of the values that I found to work the best for this setup. We can try maybe increasing the P a bit, but you can see that it doesn't like that with this setup. So let's just stick with 0.1 and 0.9. But if you try doing anything with the value for the derivative part, you just get a bunch of noise. So we will essentially just use a PI controller instead of a PID for this setup, for the speed controller. So let's say 15,000 counts a second. You can see on the graph here how it tries to actually reach that speed. We can also go and do lower speeds like 1000. And you can see that it follows the reference rather nicely. And if you look at the motor itself, you can see how it's spinning slowly, and we can of course increase that and so on. So that would be the speed controller, but what about the position controller? And activate it like this. So it's fully stable now. As you can see, we can zero it out again, and let's say we want it to reach 360 degrees. So that would be the new reference, and you can see if I just jiggle this a bit, you can see, it's not that stable. What I wanted to show you is, let me just zero out everything again, how sensitive the actual encoder is, that if you just jiggle it a bit, you can get a bunch of data on it. So let's say we put 360 degrees here. That's the reference we want to reach, and let's just increase the p-value. And that was rather fast, so let me do that again for you. Let's go back to 0. Keep an eye on the motor. That's a full circle, and if we do 360 again, so you see that even just a P controller for a case like this works rather nicely. It's not going to be the best for some smaller movements where you really want it to be accurate and it's not that stable. Stuff like that can happen, yeah? But if we add a bit of integral part as well, let's also zero it out to calm it down. And even a bit of derivative. These are some of the values that I found to work nicely. Now if we increase the... You can see how nicely it follows the reference wherever we put it. We can of course not go multiple circles and things like that. But yeah, there are some instabilities. If we would focus on the... Let's actually check that. You can see a bunch of oscillations here, and you can see that it's slowly starting to drop. That's because the accumulator has filled up of the integral part since it had to spin up a bunch. And then you can do some special other kind of stuff like gain scheduling. You can rate limit the actual PID controller and other stuff. But yeah, this is just some of my idea with this video, and this part of the video was just to show you some of the prime examples of working with PIDs and how they work. So yeah, we got it to work rather nicely for what I wanted, to do some actual speedy control, like essentially an RC servo motor. Thanks so much for watching. I'm really happy with how this PCB turned out. You can find all of the files, so everything from the schematics, Gerber files, codes and everything else down on Element 14 community, as well as on the GitHub repo. My next plan is to integrate 2 of those boards into this robot platform here, so we can get really precise control with its wheels and also do mechanism wheels on it. If you have any other suggestions of what you want me to do with this robot or with this PCB, please let me know down below or on Element 14 community. Until next time, see ya!